ideally, if all three are conflicting, you will have a Pareto optimal surface, right? A three-dimensional surface. In such a situation, you will have a curve. Okay? So we have all kinds of test problems like that. So we then say F1 and F3 are correlated. So there is no conflict between them. The optimum of F2, F1 gives you the optimum value of F3 for F1, F3 relationships, but there is a conflict between any one of them and F2. So then your surface degenerates to a curve, but that's also Pareto optimal curve. Okay? So you just reduce dimension if that happens. And in many problems I have seen from industry, if you have 10 plus objectives, easily 2 or 3 or 4 of them gets correlated. And you don't know beforehand that they would be correlated. Once you run it, then you see, I got only 5-dimensional Pareto front, whereas I was dealing with 10 objectives. Then you realize that some of them are correlated. And on top of it, what happens, if you take some random points, you will probably not see any correlation. But as you go towards the Pareto front, all the structures tries to show up. And then you see that, oh, these are correlated with that, and that is correlated with this, and the dimension reduce. So we have suggested some dimensional reduction methods. As you go along, you learn which objectives are correlated, and you reduce your dimensions as you go along. So yeah, all kinds of things are there. Okay, let's continue with this. So the classical generating methods then, what it says is, after we parameterize, we will use a single objective method, and we find one Pareto point. And then we parameterize in a different way, and we have to start the algorithm again, and we should get another point. Now, when you parameterize this one way, and you start with the initial point, let's say you're doing a point-by-point method, and you went all the way towards the optimal point, you have to overcome local optimal point, infeasible regions, and all that, right, before you come there. This is a sketch that I have drawn here. What I'm trying to say is a lot of hurdles you have to go through before you get to the Pareto front. Now, then you got the result, then you reparameterized it, and start with another initial point. All this knowledge that you had is lost, completely lost, because it's a new run now. Again, you have to learn how to overcome these local optimum, the infeasible regions, and all that. It's the same problem you're solving. It's just that it's been parameterized, so the structure inside doesn't get changed, but you have no memory of it. So one thing to say, yeah, I have to run it 10 times to get 10 points. But another way of saying is, every run is now you have to learn the same thing again and again. There is no memory. So computationally, it's a waste, right? Not only it's a waste that you have to do so many times, but also that you cannot utilize the memory. Okay. So these are some issues with the classical generating methods. Then the other way of solving it is through an evolutionary way, where if you have the same problem, instead of converting it to a single objective, what you're saying is, no, we're not going to do that. We are going to find a representative Pareto optimal set. And once I found this set, then I'm going to choose one from it. Now, if you think of, for example, a car choice problem, okay, if you have a car choice problem where cost you have to minimize, and let's say some kind of comfort you have to maximize, then what do the automakers do? You know, you go to an auto maker showroom, you will see that there are lots of cars. Their price tags are already there. These are, to me, each of these Pareto optimal solutions. Cost is one objective, so you have a smaller cost solutions, and then when you ride it, you know how it is in the comfort, or you read in the magazine of each of these cars, you get an idea about their fuel efficiency, their comfort, their safety. Those are the opposing or conflicting objectives to cost. So that's how the automakers do, or any of the consumer products that we have do, that there are more than one solution. If you go to a departmental store, right, like big malls, you will see a kitchen mixture, for example. There are so many variants. One of them is cheap, the other one is twice the price. So you wonder, why would someone buy and spend 2 times the cost to buy an expensive one, right? But those are getting sold, otherwise they wouldn't have kept it, right? So people have different needs and different pocket. So there is a product for every person, right? So they cannot have it for one product for every person, so they have few. But the whole idea is that they're following this multi-objective route, okay? That they've come up with a number of solutions, and when you go and buy the car or buy the kitchen mixer, you are the decision maker. You are then choosing which point that I should buy, which solution or which product I should buy, right? So that's a nice way to solve multi-objective problems in a collective manner, where the users are the decision makers. Okay? So you see that there are two phases in this. One is the optimization phase, where you take the problem, optimize, and go and find the number of points. The second is a decision-making phase, where once the optimum points are found, somebody has to make a decision to choose one. Okay? In the classical methods, they don't do this way. They do the decision-making first. Right? Once you have chosen W1, W2 and all that, you've already made the decision without having any knowledge about any solution. And then you optimize. So it's just the opposite. So if I go back to that slide here, this is that one. So this is the decision-making phase, and this is the optimization phase. So decision-making first, optimization later, but that may not be very practical, as I said, to choose, to provide what weights you would choose. And plus there are other issues which I'm going to talk about. But this method that we are trying to follow is you try to don't make any decision first, but you get an idea of what are alternative solutions, and those solutions can give you ideas of which one to choose. Okay, you have a question? Yeah.
Which we are calling the in particularly optimization problem, we are always compromising one to the for the another.
Yeah, but each one of them is an optimum. So I gave you the definition, right? But I think I skipped 3 slides in the beginning. Somehow these were not added in your slides. But so this is that car one that I was talking to about. Cost you minimize and comfort you maximize, let's say. So you get a car that may look like this, which is the cheapest car that you can get, but you compromise on your comfort or safety. On the other hand, if you go for another solution, which is maybe 10 times more expensive, but then you get very good in comfort. So that's the trade-off. Now, let's say if anybody can come up with any car, they will fall into this blue region. This is again hypothetical in this space. Okay. So if I am producing this car, which actually cost me so much for you to buy the car, and you get only this much comfort, and there's only some automaker is producing this car A, which costs only this much and has a better comfort. So this solution is better than this in both objectives, then nobody will buy my car, right? I have to go out of business, right? So in that sense, this point is not an optimal point. Now, can we say this point is an optimal point? I will call it an optimal point if in its vicinity or in the entire search space, I don't have any other point better than it, right? Then it's an optimal. Can you show me any other point which is better than this with respect to both objectives? In that case, I have to take a paper and now put the right bottom corner here, because I'm minimizing and maximizing over here. So the paper goes here, and I have no point here. Same thing I could do it on B. Same thing I could do it on C. There is no supporting points here to dominate it. So all of the points on the red line here is theoretically, each one of them is an optimum. And I give you the verbal argument of why these are optimum, because you can give me any other point from the search space, any other solution from the search space. I can always find a point from the red line which is better than that in all objectives. Unfortunately, there is no one. So if you give me one, I have to give you one. If you give me another one here, I have to give you another one here. So it's an optimal set. But 2 points from the optimal set are one is not better than the other with respect to all objects. So unfortunately, in this problem, there is no one optimum point. There are multiple optimal points. Like we talked about in multimodal problem yesterday, right? You have a function where there are a number of global optima. You cannot say which one is better. All are equally good. So what you can do best is find as many of them as you can and switch from one to the other. But here, there are multiple solutions, but there is an objective trade-off that we get. There we had only one function, objective function, so there is no trade-off. But here, the number of solutions come because of the trade-off in the objectives.
Sir, can't we say that B is better than A?
Why? How? With respect to both objectives, B has a larger cost than A, right? B is optimum maybe for you, but A may be optimum for another person. So that's how it is. Exactly, but theoretically speaking, all of them are optimum, because you cannot find any other point in the search space that is better than that in all objectives. Is that clear? Okay. I think I missed some key slides in the beginning. That's causing all these questions, but it's good that you're asking. All right. So this is the philosophy that we follow then in evolutionary methods, that we are going to find a set of points first before making any decision, so that we have a knowledge of the range of points, and then we can make a choice of which one we need eventually, right? So if you're thinking of now only the optimization part of it, if you're focusing on the optimization part, what should be the goal of an optimization algorithm? Because there are more than one goal, more than one optimum that we have. First thing you need to do is have an algorithm that converges to the Pareto front. You can't sacrifice on that. For example, if you get a set of points that has a very good distribution, but none of them is close to the Pareto front, these are not useful to me, because none of them is close to being optimum. I can give you much better points here. Okay? And then if you say, okay, this set of yellow points where everybody is a Pareto optimal point, but they're only concentrated on one part, it doesn't represent the whole front, then this set is also not good. So we are not talking about the whole set. How good is the set? We need to have both convergence as well as a good diversity. So these black dots, the points that you have, if any algorithm is found for this problem, that's the ideal algorithm, because they have converged and they show the whole Pareto front in a nice uniformly distributed manner. Is that clear? So this distribution aspect we didn't have to do in single objective. We are always concentrating on convergence, how close we get to the optima. Here, not only that, that's important. In addition, we also need to have my set of points, my population members should be well distributed. They should not all crowd around each other. That's where we need to use some kind of multimodal optimization as well, so that we can find multiple well separated points. Okay? All right, so that I've already talked to you about. The EMO philosophy, because it's a population approach, we are not doing one by one, has this advantage that when you're dealing with a population, and let's say by selection, recombination, mutation, I got something, one of the members coming closer to the Pareto front. Now this member becomes a super individual in the population, right? Once it's there, this is, as I was telling, belongs to the first front, and maybe second front, and so on and so forth. But importantly, this has a chance to mate with other population members, because this will definitely have more than one copies. So you have more than one chances to cross over, and crossing over between this and this may create a point here. So this will bring all the solutions down very quickly. That's the parallelism that you have in a population based methods, which we didn't have in the classical generating methods, because there is no memory. So this is a hand waving argument again of why evolutionary methods gets so fast and get to the Pareto front compared to classical methods. Okay, there are various classical other methods. This is one which is pretty well known. I wanted to just tell you the name of it is normal constraint method. It's a generalized version of the epsilon constraint method. Now in the epsilon constraint, your constraints are always on F1 or F2. Here the constraints are along these lines. So if you minimize F1, you get that point, minimize F2, you get that point, join them with a line, and now your constraints are always orthogonal to the line. So your epsilon will move along that line, and you say left side or top side is feasible, and then you minimize F2 and you should get this point. So you can also get the non-convex points by this method. It's a little general, so it works a little better. So what we have done is we have used this method on 3 different problems. One is, I'm going to show you this. This is a 30 variable problem, test problem, where the front is non-convex. So some of the weighted sum approach will not work. Weighted sum approach will only find this point and that point, the edge. There is another definition of Pareto optimal points are called weak Pareto optimal points. So all these points here have the same F1 value. This is F1 and F2, right? Same F1 value, but F2 is different. According to our definition, this point, which has the lowest F2, dominates this point, right? How? Because you see, this is same as that. So this point, if it's 1, that point, if it's 2, then you're saying 1 is equal to 2 in F1. It's not worse. 1 is not worse. It's equal. And 1 is better than 2 in F2. So 1 dominates 2. So according to our definition, these points do not exist. But there is a relaxation in the definition with a strong dominance kind of concepts, where you say this one will not dominate that, as long as if one is equal, they cannot dominate. Okay, because at least in one of the objectives they're equal. Other it can be worse, but since one objective is equal, one cannot dominate the other. So there is a loose definition that exists that gives you a weak Pareto optimal front. So all these are also now weakly Pareto optimal.
Sir, in this figure, sir, we are minimizing F1 and
Yeah, always by default.
Sir, how they are then conflicting?
Because take this point and that point. Okay, this point has a smaller f1, larger f2. This point has a smaller f2, larger f1. So anything you see of this shape for minimization is a conflicting front. Ideal point is here. Ideal point doesn't exist because all the points search space is here. Okay, so they are conflicting. But these ones in practical purposes gets dominated by one. But as I said, mathematically there exists a weak Pareto optimality. And this algorithm that I just talked to you about, NCM, cannot distinguish. So it will find the weak Pareto optimal point. So when I use this for 20,000 evaluations, it actually finds all these weak and then these points. You see how nice a distribution it gets. It's not has lots of local Pareto optimal fronts, and here is the global Pareto front. As you can see, there's a little line here just appearing, and there are actually 100 different fronts here, 100 local fronts where you can get stuck, and this algorithm got stuck somewhere here around midway after 100,000 evaluations. This is the problem with the classical methods because it can get stuck with the local front, and we used fmin_con here, so it just gets stuck over there. This is another problem where there's three objectives, f1, f2, f3. Now you have a surface. This is the Pareto optimal surface. After 100,000 evaluation, this is the status of all the points. They haven't, some of them have come to the Pareto front, but many of them are yet to come. So if I keep running for further number of evaluations, they will eventually go. But I wanted to have a snapshot. 100,000 is too many function evaluations. I thought, let's see where we are at this point. So I will talk to you about NSGA-II, one of the EMO methods. When we try that, on the ZDT problem, we don't get the weak points. And you see the same number of evaluations, we also get a very good distribution. Okay. This problem where we are stuck around 50, now we are on the global Pareto optimal front without any change of the method, because our methods are more global than the classical methods. They don't get stuck into local fronts. And this was the surface problem, three objective problem. You see all of them come to the surface and gives you a good representative view of the surface. You can see some gaps here and there. We now have NSGA-III, which is much better than this. I will show you the results of NSGA-III on this problem, same problem, which is much better distribution. Okay, so I haven't given you the algorithm, but shown you the difference between a classical way of doing it versus an evolutionary, just to make the point home that there is an implicit parallelism that goes in a population-based method, which the classical methods cannot harness. And that's why you end up spending more evaluations, or the same number of evaluations, you end up not reaching the front or something like that. Okay. I think I'll give you a break now for 5 minutes, and then we'll start with one of the algorithms. this kind of fronts.
So
If you do any other, it may this or this. People are not used to seeing this thing. So you can always present it this way. So if this was maximum in your new place, and so yeah, but we're still collaborating on some papers which we started to write and still working on it. Okay, we are back. All right, so let's continue with an algorithm based on GA to see how you can then solve this multi-objective problem. So this is the flow chart of a genetic algorithm, right? So we start, there is the initialization of population. Okay, you remember the flow chart we started with generation counter 0. Here I'm showing you in a flow chart form. Termination condition, if yes you quit, if not evaluate, assign fitness, reproduction, crossover mutation. Reproduction is selection, crossover mutation, increment counter go into the loop, right? Okay, the only problem in multi-objective now is assigning fitness, because once you assign the fitness, well, when you compute the objective functions, you have f1, f2, f3, all these vector now. You got a vector of objective values. Previously we had one number, so we could just see which one is better. Now the question is, how can we come up with one fitness? Because ultimately when you have two things, you have to say, you can do whatever, but can you define this whole thing as a fitness function? What is that fitness function? That should utilize all the objective vectors and the constraint values as well. So we'll look at one at a time. Constraints will move for later, but just how to handle the objective values. And we already talked about domination. Domination will come at our rescue. But when we emphasize dominated points, this can ensure us that we'll go towards the Pareto front. But will it ensure us that we are going to get a diversified solutions? The answer is no, right? We need to do something. As we had looked into the multimodal scenario, that we have to do this niching, the sharing function kind of approach to maintain multiple solutions. So when you want to maintain multiple solutions, we need to have an additional sharing function approach. So both these needs to be considered. Emphasize non-dominated solution for convergence. Emphasize less crowded solutions. This is what we talked about yesterday. When you want to get number of optima, the ones that is less crowded, we have to emphasize it, right? By dividing it by niche count and all that, right? Similar things we have to do here. Okay. Now, we talked about the domination and non-dominated solutions and all that. Let's talk a little bit about the less crowded solutions. We have two spaces, right? One is the decision space, x1, x2 space. It has its own bounds. There are constraints that restricts and everything. So let's say this is that feasible space. There are three variables. So I've got a three-dimensional feasible space. Any point here is feasible. Now that point, when I evaluate, let's say there are two objectives now. I get a point in the objective space. So when I take each and every point and try to see how this looks like, this will have a character. This will have a shape, right? So this is called the objective space, and that's called the decision variable space, or just simply the search space or decision space. Okay. Now every point from here is mapped here. This is, you cannot search here. These are objective values. You have to always search here. Okay. And the result is shown on this space. Okay. Now the crowding I can look at now in two spaces. Now that suddenly I have an extra space, the crowding can be here. For example, out of all, if these are my population members, this is a crowded, less crowded point, right? Because there is nobody around it. In this space, this one also another less crowded point. There is nobody around it. These are crowded. On the other hand, if I look at the same set of points in my decision variable space, these two are isolated and less crowded points. Now it could be that this one is not mapping to this. This one is mapping here. And one of these is mapping here. It could be that. If you have a sufficient nonlinear objective functions, right? It can be. Or it can be that this one is mapped here and this one is mapped here and there is a one-to-one. If you identify less crowded, that's also less crowded here. Most cases it happens, okay? But some weird cases where there's a lot of nonlinearity linked in the objectives and variables, this kind of thing can happen, that this one goes there and one of them goes there. So there is no crowding in X space, but crowding in the objective space. Then the question is, which space you want to do that calculation of the distance that we needed for the sharing function, which space you want to do. So what would be your choice? Okay, let's talk about decision space. What if you do here? So what will happen eventually? If you maintain diversity in this space, this is the decision variable space, the x1, x2 space. So the solutions that we'll get here will look completely different because x comes up with the phenotype of the solution, how it will look like eventually. So they will look completely different from each other. You'll make sure that's going to happen. Okay. When you do it here, well, there may be all of them are slight differences if they're nonlinearity, slight differences dimensions, but that slight difference causes a big change in the objective value. So you'll get a very good spread on the objective values, the cost-wise and the waste-wise or efficiency-wise, they are quite different. But if I go back to the solution space, I may look they are not much different. It's just certain key parameters are slightly different from each other. It can happen. So which one would you prefer? Is there any preference, or it's difficult to say? Objective space over here. Everybody agrees? Well, there is no unique answer, right? If I'm an engineer, I would like the spread in my solutions so that I see them very, very, very different looking. Although I may not have good trade-off in the objectives, but if they're different looking, that's what I'm interested in. Actually, I'm interested in both, but a little bit preference to maybe the decision space one. But to most people who work on economics and computer science related area, they prefer the objective space diversity. Okay. In most of our studies, we do in either of them. Most studies do niching in this spacing, not this space, not in this space. Okay. So my NSGA algorithm that I started in 95, 94, 95, were doing niching in this space. But then on, I saw everybody is doing niching in this space. So NSGA-II now does in this space. Okay, NSGA-III also does in this space. So I just switched to this. But then once in a while, we work like the Omni optimizer does in both spaces. That's another advantage in Omni optimizer, is that we do a collective, we do a average crowding in this space and that space together. But that's an important decision that you have to make before you come up with your algorithm. Okay, a little bit of history of how all these multi-objective evolutionary methods have developed. Very early on, before even 84, people have been talking about multiple objectives, and there is a need in practice, but nobody really suggested anything. First, 1984, this person, Dave Schaefer, he was doing his PhD on this topic. He called VEGA, Vector Evaluated GA, because he considers the objective values as vector now. So he came up with some suggestions. Very simple idea. I'm going to show you what he did. But unfortunately, his algorithms were not able to maintain a very stable subpopulation, at least his early algorithms. So people realized that, oh, it's a difficult problem to solve. Then Goldberg, in his book in 89, he always comes, right, in every key events in this field. He made a, now let's see what I did. Okay, so he made a 10-line suggestion in his book about how to make a multi-objective algorithm to involve the non-dominated, emphasizing non-dominated solutions and less crowded solutions. He came up, he actually suggested, he didn't simulate anything, but this is just a suggestion he did. Then 3 groups of researchers have picked that up, that his ideas, and 3 different algorithms came around 93 to 95. So MOGA is by Carlos Fonseca, worked with Peter Fleming in UK, in University of Sheffield. Peter Fleming is still continuing to have PhD students in this area, still working. Carlos Fonseca went back to Portugal, and he started working in this area. NSGA was ours from IIT Kanpur. There's Srinivas, who was my master's student. We developed it with that. And then Goldberg continued with Jeff Horn in US, and he suggested NPGA. So all of them were really using Goldberg's idea. And all of them worked on the problems that Schaefer could not solve, could not maintain. Okay, so all of them could solve it, and they also did some more problems to show that, yeah, they are more generic than that. So around 95 onwards, people came to know that there are ways to handle multiple objectives. After that, there are some suggestions, but a major breakthrough happens around 2000 onwards, because all these methods, that's first phase of methods, as I say, first generation of methods, they did not use one thing, which is the elite preservation. Okay, I'm going to talk about that a little more. So they are non-elitist algorithms. So in my book, I classified them as non-elitist methods. Then elitist methods came up, where good solutions from previous iterations were emphasized. Okay, were directly put in. Okay, so those methods, the NSGA-II belongs to that, and SPA was another very good method, still very popular. It's called SPA-II now. So these methods are more popular. Well, since about 2000, 2008, 2009 onwards, not 2008, 2009 onwards, people have started paying attention to many objective optimization where you are interested in more than 4 or 5 objectives. So then some of these methods are not good at those. These are good for 2, 3 objectives, 2 objectives or 3 objectives. You can look at the growth, and I kind of stopped it after 2009. You can see that Vega was here. There were hardly anything over here, 1 paper only every year, and that too after many, many years there's 1 paper. But this one onwards, there are regularly papers that are coming up, but not again at a high volume. But after these 3 papers were suggested, there is a sudden increase, and you can see the increase. This is up to 2008, 2009, you can take it, but it's continuing. It's still continuing. So it's really a very fertile and open field. A lot of people are coming into this. So these are mostly non-elitist methods: Vega, vector optimized DA, weight-based GA, and actually I have a multi-objective optimization book as well. It's available in India as well from Wiley. We talk about most of these methods in that. Okay, I'm going to just talk about Schaeffer's Vega and maybe some hints of NSGA. So it's a very simple-minded method. What you do is if you have m objectives, let's consider m equal to 2 to start with. There are 2 objectives. You divide your whole population into 2 halves. Okay? First half you evaluate using F1, second half you evaluate using F2. As simple as that. And he was using, at that point, tournament selection was not there, 1984. It came out around late 90s. Well, late 80s, beginning of 90s it came out. So this wasn't available in 84. So he used proportionate selection, okay, to individually to the subpopulation. Recombination he used on the whole population. So then the partition is not there. Mutation, of course, is an individual thing, so you can mutate any individual. So only thing is that if you have 2 objectives, you divide the whole subpopulation into 2 subpopulations. One is evaluated by F1, another is by F2. That's it. Is that clear? And selection is done independently on that. Okay. So we simulated in back then when we were developing NSGA, so I don't have the new results. Maybe I should ask some of my students to create some new results to have little nicer plots. But here is a problem with single variable 2 objectives. Here is the Pareto front. Okay. You can see that starting from here, this is after 10 generation, there seem to be a subpopulation setting up, right? There is a lot of points setting up on the Pareto front. But if you keep running, this is, I think, after 50 generations. Already you start to see clustering started to happen. After 100 generation, you have 1 point here, 1 point here, and 1 point there. So if you keep on running, this also goes away. So you just have the individual champions. Can you explain why? Why you are getting to the individual champions? So this is best for F1, and this point is best for F2. Why I cannot maintain these intermediate ones with this method? Yeah, we just divide it. So some of the members are evaluated based on F1, so these are good solutions for that. Some of them are for F2, so these are good solutions for that. Nobody was evaluated for intermediate. So intermediate solutions have no way to go, so eventually they die.
So but for the crossover thing,
yeah, crossover can create point here, but selection weeds them off. Because selection is based on either of the objectives, so there is pressure towards the edge. Okay. So he actually thought that way, that crossover will always keep it. But it kept it for a while, you see. But then when you keep on running, solutions eventually gets towards his own optima. So he had a couple of more suggestions, I think, which I have here. He introduced non-dominated selection heuristics. It's a little complicated. He's manipulating with the way you assign copies in proportionate selection. But that also didn't end up in getting a very stable subpopulation. He did another thing with the mating. He thought maybe you should control with the mating, but that also didn't work. So in some sense, he had a nice thesis where he did a lot of studies, and he kind of elaborated that, okay, this did not work, this one went a little far, but at the end, we still need better methods. But this was the first study which actually showed that you can try, but then there are some more things needs to be done in an evolutionary method. That's probably the reason where 84 till 89 till Goldberg thought about it, and 84 till 93, 94 for good 10 years, nobody did anything with that. Okay. There are some intermediate ones. This was one by Hazela and Lin in US. They were working on single objective GA, but these people are engineers. Hazela is a professor in aerospace, very well-known person. And with his student, he came up with a weighted sum approach. So what he does is, for every solution in the population, you also have a weight vector that you keep coding. So when you compute its objective value, you use its own weight vector. So weight vectors are initialized randomly between 0 and 1. And then to get one objective value, you actually do a weighted sum. And weights come from your string. And that becomes your fitness. So then different weights. So he's maintaining a diversity in the weight vector. And the x gets automatically adjusted. So he was successful quite a bit with that. And in my book, I showed you some such plots to explain what's happening. Every solution has its own weight. So, and we finally did a simulation, and we could see that for 2 objective problems you can maintain. But nobody really followed it up. Nobody did that for 3 objectives and higher number of objectives. So, and it's a bit messy because you also have to code the weights. If you have 10 variables, if you have 10 objectives, then there are 10 weights, and then you may have 20 variables. So 20 variables plus 10 weights. So that's each of your stuff, and then it kind of gets messy. Let me talk to you about NSGA, very briefly the principle. Here we actually took the sharing function concept literally to Goldberg's idea. So you create these x's, either with binary strings or whatever. You have these x's. Compute the f1, f2 values. Now do a non-dominated sorting. So we were the first to use a non-dominated sorting method, complete sorting. So if you sort them, let's look at f1, f2 in this 2 objective space. So here is 1, 2, 3, 4, 5, and 6. These are the points, minimizing f1, f2. So if you do a sorting, 2, 5, 4 is the best non-dominated front. So this is the non-dominated front level 1. Discount it, and then again do a non-dominated identification of non-dominated points. It will be 1 and 3. So these are second level. This is the third level. Okay. So to me, these are much better than this. These are much better than that, right? Because this is where the front is. All right. So what we do is identify first the front. So you see the 2 and 4 and 5 are in the first front. So this is the front number, and 1 and 3 is in the second front, and sixth one has front 3. Okay. Now what we do is we come up with a fitness scheme. All the ones that are 1 we first consider and assign a fitness equal to the population size. So if there are 6 members, we put 6 as the population. This is an artificial number. 6 is the population as the fitness for all 3 of them. And then we go, so this is, so by putting a population size equal to population size, and then the other front members will have less than the population size, and we are maximizing, we make sure that these front 1 members has the highest fitness. So this gets highest fitness. So this takes care of the convergence. To maintain the diversity, what we now do is go to their X space, only this 2, 5, and 4, only this class, this set, and do a niching. That means look into their neighborhood for crowding and divide this fitness by the crowding, by the niche count. The same exactly the way we did the multimodal. So you see that in this case 4 and 5 are crowded. So their niche count will be more than 1. And 2 is isolated. Its niche count is 1. So the 2, 1, I divide by 1 and I get 6. But 4 and 5 I divide by more than 1. Based on their closeness, I get from the x values, so I get 3.43, 3.43. So now, although these have the highest fitness, 6 is the second one is the highest, and 4 and 5 is the next highest. So I have put a convergence preference and also points that are isolated preference for them. Okay. Then we go to the next set. So I go to the 2 then. I look at which one has the minimum fitness. What is the minimum fitness of all these first front members? I find it's 3.43. So this ones I assign something smaller than 3.43. So let's say I assign 3 to them. Okay, so that these are better than any of these. And now and go and do the niching in this space, in these 2 spaces. It so happens that 1 and 3 are wide, very far away from each other, so they don't affect each other's niching. So I divide this by 1 and divide this by 1, I get 3. Then I go to the next one and I will assign something smaller than 3. Let's say I assign 2 or 2.5, so that becomes that. So if you look at now these numbers, it says second one is the best, then 4th and 5th, then 1 and 3, and then the last one is 6. So now if you do a proportionate selection, this will have more than one copies probably. This will probably have no copies, and these two may not also have any copy. So now I've got given the right pressure, and the whole thing then works very nicely. So here is the same problem. As you see, after 10 generation, we've got already quite many points. This is 50 generations. This is 100 generations. You can keep on running this. You will always have points here because we are doing a non-dominated sorting. So anytime you have an isolated point in the X space, you have isolated point, it becomes the best in the next generation. So suddenly it will have 2 copies or more than 2 copies by the proportionate selection. Yeah.
We are working in objective space.
Right.
So why we are not using sharing concept?
Yeah, this one I'm not working on objective space. I worked on the decision variable space. So as I said, original NSGA algorithm is niching on in the decision variable space. But you could do this space. All the fitness assignment has to be different. Okay. So this algorithm was probably one of very, very few algorithms which use niching in the X space. And the reason I told you, because I want to get different looking solutions. Okay, but now I have also switched to niching in the objective space. But usually there is a correlation, right? So it doesn't matter where you do it, but some problems can be a little naughty, and you have to then do it the right place. Okay, we tried many other problems, so let me not go into all that. Let me skip other methods and straight away come to the elitist type of methods, where there are again many different methods that exist. I'm going to talk about only one, that NSGA-II, or maybe SPA-II also a little bit, SPA. So what is NSGA-II? It can do 2 and 3 objective optimization well. More than that, all of these methods have their weaknesses. Then we'll talk about many objective algorithms later. This is the first method. So the NSGA has a parameter. What is that? Sigma share. I still need that sigma share to say how to compute the sharing function. That was always troubling to me, that we should take it out. So in NSGA-II, we don't have any parameter other than the population size, crossover probability. Those are standard parameters for any evolutionary method or genetic algorithm. We don't, because you're doing multi-objective, there is no extra parameter that I'm asking here. That's really one of the main reasons why it is so popular. But it's also modular, okay? And the bottom line is, for 2-3 objective, it works. It just takes you in the right direction. So this is coded in many different softwares. It has, this one I think I did a few months ago or maybe last year, but now it has crossed 20,000 citations. So it's really, very popular. So how does it work? Okay, I'm talking about one iteration of the algorithm. So here is my current population. Okay, now I have to do PT plus 1. Okay, so in that process, I create an offspring population of the same size by using selection, crossover, mutation. It's a GA I'm doing, so you know the process, right? Selection, recombination, mutation. So we get that. Once we've created the QT, I combine PT with QT, and I have a combined population called RT. So it's double the size. These are already coming from before. All objective values are known here. These are new points. I have created the objective function values. I combine them. Now I have 2 times the population size. First thing I do is do a non-dominated sorting of the whole population. Actually, you don't have to do the whole population, but you start identifying the best non-dominated one, which is F1. Okay, they are here, let's say. Now here, if some of the parents are still good compared to children, they can surface up here, because you're doing a non-dominated sorting of the whole thing. You're identifying what are these members in this entire population which are not dominated by any other member of the population, the entire population. So it could be some from here and some from there. So that's the elite preservation. Something that was good will go on. Okay, all right. Then F2, which is the second level of non-domination. We temporarily discount them from the population and find the new set of non-dominated. That's that. Then F3 and so on and so forth. Now, as you are getting F1, F2, you also keep a note on the size, because F1 you are accepting for sure in your PT plus 1. F2 you are accepting here, like for sure. And then you are keep on adding these numbers and saying, have I crossed the population size? If not, I will continue to do. A point will come where the whole front now cannot be taken in, because if I take it in, my population size will increase. I don't want that for an algorithm to population to increase, decrease, so I will not be able to keep track. there is another reason for that also, which is come with the crowding distance. So I want to keep my population size same. So that means I can only choose few from it. Remaining I have to reject, and all those points that are still not, I have not made front M yet, can be rejected because those are bad solutions. So that's where I'm answering somebody's question that said, do I need to do all the way? No, we don't need to do all these. Okay, you only need to do few levels of non-domination and N. In fact, what happens after a few generations, F1 becomes so large that this becomes more than N. So you really don't have to find F2, F3. F1 itself is big enough, more than N. Okay, so the whole F1 you cannot take in actually. Yeah.
When we are going to the F3,
Mm-hmm.
so which point we have to reject?
Okay, now I'm going to talk about that. So let's see what we have done up till now. We have done elite preservation because anything good here is going to come here. We have given emphasis to non-dominated points. The best points are already accepted. So we have chosen the best non-dominated points. So that's how we're emphasizing non-dominated. What we have not done yet is emphasize for less crowded solutions. That's what we do in this set. So we are going to be choosing those that are widely distributed in its front, in that front. So we do a very cheap way over here in this slide. So let's say that I've got lots of other fronts. This is that third front that I cannot take everybody. There are 1, 2, 3, 4, 5 solutions. Let's say I can only take 3 out of the 5. So the question now is, which 3 I should choose so that I have a very good diversity among them. They are not crowded. So which 3 do you recommend? Maybe the 2 extremes and 1 in the middle, maybe this one, right? This, and this will make a very good distribution. If you take these 3, then it's not a very good distribution because you're not covering the entire front and they're all close to each other. These 3 again, not very good because you're not taking the extremes. So what we do to have this is you introduce the crowding distance. Let me see if I have that here. I have a problem to show you, but here is what it is. We go objective wise, we go. All right. So for every point, we first sort them in the increasing order of F1. So this will be 1, 2, 3, 4, 5, right? If it's one of the extreme points, that means there's nothing on the left side or nothing on the right side on my sorted list, I put an infinite crowding distance for that. For this one, for example, my left side member is that, my right side member is that, right, in the F1 sorted list. So you can just drop a projection on F1 and see that they're sorted, right? For this one, what's the difference between the 2 sides that I have? So if I am here, I will look at my left neighbor and right neighbor and look at the difference, which is this distance, right? Okay, store that. And then move to F2 and do the same thing. So sort them from smallest to highest. And when you come to this guy over here, what is the left and right? What is the difference? It is this, and the difference is this now. We simply add the 2. And that becomes the crowding distance of this point. Now, obviously, since we are adding 2 objectives, we need to normalize. And in GA, there is an easy way to normalize is that we have the maximum and the minimum for both F1 and F2 for the entire set here. We have F1 max, F1 min. We have F2 min and F2 max, right? And we can normalize all those between 0 and 1. So this will become 0. So the ideal point of this will become 0, 0. And the nadir point of this will become 1, 1. Right? So everything is kind of normalized. Now I can add the 2 numbers. And that becomes my crowding distance. Okay? So each point I can now compute the crowding. So see, for this point, the crowding distance will be this plus that. For this point, it is this plus that, right? For this point, it is this plus that. And for the 2 extremes, they are infinite crowding distance. Now what I do is sort all these members in a decreasing order of crowding distance so that these 2 are on the top. Then which will be the next one? This one. Then the next one will be that one. And then this one. So this gives us an idea of the crowding, right? And then what we do is go from the top of the list and choose as many as I want. As many slots are available. So as I said, if there are 5 members, 3 slots that are available, I'm going to pick 3 from the top. So this takes this, and that one. Now questions, yeah.
For 2 objectives, we can normalize. If there is more than 3 more
No. What is the difference if I have 3?
How do you normalize? You told us the F1 mean we know.
Yeah. So for 3, we also know F3 mean, F3 max. So what is the problem of normalizing F3?
We were normally normalizing the formula is for 2, right?
No. Every objective is normalized independently. I need F1 mean and F1 max, and I normalize F1. So this becomes, this has a 0 value, this has a 1 value. Then I go to F2 and I minimize F1, this becomes 0 now. I minimize it, the minimum value of F2 becomes 0 and maximum of F2 become 1. If I have F3, I do the same thing. If I have F100, I do the same thing. No problem. Other questions?
Sir, what if we calculate the Euclidean distance instead of calculating
Sorry, what distance? Euclidean. Yeah. Euclidean distance is, so what is the complexity, the algorithm that I mentioned? So how much complexity is to sort? N log n. If there are n points in this front, there will be n log n. Let's say I've got all population members are in this front, so there are n members. That can be the worst case. So I have n log n for each objective. So if there are m objectives, I have m times n log n complexity to do the sorting, and then one more time I sort to choose the top something. So there is m plus 1 times n log n. That's the complexity that we have for doing this. Now as soon as you do Euclidean distance, you have to do from this to this, from this to this, and all of them you have a n square computation. It's not n log n. So your algorithm is little more expensive. If n is large, it's going to be a little expensive, but you can then get a little better distribution. So that's why I said right in the beginning, this is a cheap way of doing, very quick, computationally quick way of doing it. But then there are other methods, like you mentioned, Euclidean distance is another extension of NSGA-II, where you change the crowding distance with Euclidean distance. Not so. This is defined as the crowding distance, the sum. If you want to visualize, it's like this. For every point, we are trying to put a box touching the neighbors. What is the box size? What is the perimeter of the box? Half of the perimeter, really, of the box. So this one, you need to put a bigger box to reach the 2 neighbors. This one, you need a smallest box in this case. This one, other neighbor is at infinity, so you have to have an infinite size box. So the size of the box is your crowding distance, and you want to pick up the one with the larger box size because that's less crowded. Okay? This idea, although very quick computationally, but doesn't scale up for higher number of objectives. Like even 3, it is little starts to show its weakness. I showed you some results with the 3, right? 4 and all, it just messes up everything. So we can fix it with the Euclidean distance or other clustering methods. Algorithms exist, but those are more and more expensive. Like if I do NSGA-II with this and NSGA-II with clustering, which is a very nice way of doing it, you have to just keep waiting, because if you have a population of size 200, it just, you have to wait like a lot of time before it does, because it's order 200 square now. Okay, so it's have to wait quite a bit, and you are doing it at every generation once. Yeah.
There is also an excellent NSGA-II algorithm.
Yeah. So those are different. Those are doing crowding with the epsilon dominance concept, which I have not talked to you about. Those are other ways of maintaining diversity. Okay. So if I have time, I'll get to that. Okay. So is this process clear? The whole NSGA-II process is nothing more than that. Okay. So where is the parameter? Is there any parameter? No, there is no parameter here. There is no parameter in the non-dominated sorting process that I talked about. Everything is adaptive. Okay. All right. So let me show you with this example. So let's say this is a simple 2 objective problem, no constraints. I've got the parent ones are the square boxes. They are marked as 1, 2, 3, 4, 5, 6. And then the circles are my QT, my offspring population, and those are A, B, C, D, E, F. There are 6 points again. I put them all together and do a non-dominated sorting, and you see that I'm minimizing F1, F2. So A, E, and 5 are your non-dominated set, and this is actually the Pareto set. Okay, this whole thing is a Pareto set, but we haven't gone there yet. These are my points. So first front, then second front, then third front, and fourth front. So this you have to do first. After you've done that, our population size is 6 here. So first front, there are 3 members, so I can take all 3 of them. So those are taken already. Second one, I've got 1, 2, 3, 4 points. But how many I can take? 3. So I don't have to even sort these 2, but I've already done it. But the algorithmic way when I do it, we don't do that. But here, there are only 12 points, so I'm showing you all the thing, but we won't be sorting them. So these are actually deleted anyway. They are far away from the Pareto front, so they get deleted. Now out of the 4, I need to choose which 3. So I get those 4 points here, 1, 2, 3, 4, and I drew the crowding distance for that, which is this box, crowding distance for this, which is this box, and these 2 are infinite. So if I then sort them according to crowding distance, it will be 3, B, and 1. So 3B, so 3, 1, and B, and 5, and E, and A. These are the 6 members that will stay. In the next generation, others will die. And then you continue this process. Okay, so that's NSGA-II. No parameter. If I simulate it, it's not working here. I'm sure I have a wrong file. Okay, I had the other file, maybe that one. No, this is even older. I wanted to show you how it simulates. Okay, so if I go up, and let's see if this works. Yes, that works. So let me go and show you. Okay, you see, you don't see it? Why? I'm seeing it here. Why is it not coming up? Okay. All right. Let me try to open another file, which I have used. This one I've used recently. It should have opened. I changed my computer, so something has gone bad after that. I'm seeing it here. I don't know why I can't project it over there. F1. Okay. If I go to the next slide, does it show up? Now nothing is showing up. Okay, that's weird. Display, arrangement. Let's try to do mirroring. Go back to that one. This is my slide. I'll get back to it. So this is the one I wanted to show. I go up. F1. Okay, this one is coming, but it's not showing me the simulation. It should have shown me the simulation. There's some compatibility issue with my video, I think. Anyway, so I'll probably show you the simulation when I demonstrate it. I don't know when. I don't know whether I will have time to the afternoon. Anyway, so we have to just keep moving. So we'll just keep it. So let me see. I'm interested in this one, L5. Okay. So I'll skip the simulations. I'm seeing it right here, but it's not showing up. Now, when it shows up, then it doesn't. No. Okay, fine. Next one is the SPEA-II. So it's a little different from NSGA-II. What they do is you have a population of points here. You have a population of points here, and then you have an external population. Okay. Usually this is 20% of the evolutionary population, and this one are the non-dominated points of that. That's kept here, or non-dominated points found so far. So these are kept here, but this external population and the current population participate together in defining the fitness. So there is a very simple way they calculate the fitness for every point here. So for every of these x points, the external points, you find out how many points does it dominate. For example, this point dominates in my population 1, 2, 3, 4, 5 points. So the fitness of that becomes 1 plus 5 or 6. And then for sorry, I think it's just the 5. It's just the 5. And then for assigning a fitness to one of the population members, what you do is how many of these external members does it dominate, and their strength, like this one had 5, this one will have 1, 2, 3. So 5 plus 3, 8 plus 1. They add a 1 to this. So that becomes its fitness. So smaller the fitness, the better is the point. So external and population are all put together. Everybody is assigned a fitness, and then they do tournament selection or whatever. In order to have, so there is emphasis for non-dominated points. And in order to have a niching or diversity preservation, they do a clustering, which I mentioned that if you do, it gets very slow. So SPA-II really have to wait quite a bit to see the results coming. But it does a pretty good job in maintaining a well-distributed point. So that's the trade-off you have. Do you want to do it quickly so you get a rough idea, or you want to really spend quite a bit of time every generation so that you get a nice distribution? As long as you use a non-domination emphasis and care for less diverse points, you will have an algorithm. And there are many, many people come up with many different ways of doing it, and every time it works. So Goldberg, all credit goes to Goldberg, where he first pointed this out, that you need to have these two things. You cannot just assume any one of them in an evolutionary method. Then people did in many different ways, some with some parameters, some without parameters. The ones without parameters are much better. Okay, I'm going to skip the Pareto archived because there are, as I said, many, many methods. Some of them are pretty old as well. Now let's move to constraint handling and see what can happen in constraint handling. Now you have constraints. So one simple way to do is you can choose one penalty parameter for each constraint, each objective function, right? Because remember, the role of the penalty parameter is to make a balance between the two. So if your objective is changing, constraint violation is the same, but you have to adjust your R so that F is getting balanced with the corresponding constraint violation. So in single objective, you had one R to fix. Here you have m R's to fix if m is the number of objectives. So it gets a bit more difficult. Nobody use the penalty function approach. There are some early methods people suggested, but there are a couple of methods which are pretty good and do not require any parameter. So I'm going to be talking about our method, which is a simplification of Fonseca's idea. But Fonseca's idea is very generic. You can use it for solving other kinds of problems as well, like just the constraint satisfaction problem and so on and so forth. So let me explain how we handle constraints here. It's very similar to the single objective constraint handling, where there was no parameter, right? Here also we try to do the same. But instead we go and change the definition of domination. Okay. So we call I will constraint dominate J if any of these three conditions are satisfied. If I is feasible, J is not. Okay, so that means you're comparing two in your tournament. One is feasible, the other is not. Then the feasible one dominates the other one. Is that clear? Okay. Now, what if both of them are infeasible? Then we don't even look at the domination or anything. We just look at which one is a smaller constraint violation. Very similar to the single objective. And if both are feasible, that means both satisfy all constraints, then we look at which one actually dominates the other, the usual definition. Very simple change, right? No parameter again. And see the effect that it will have. Let's say I had this original problem, which I showed you for NSGA-II, the same problem, right? Let's say I've got these 6 points, and this constraint is not there. First, assume this constraint is not there. So the entire thing is feasible. So if I do a non-dominated sorting, how it will look like? Minimizing F1, F2. So which will be the non-dominated front? Let's see if you can tell me. 3, 1, and 5. That's the first front. Okay? Because 2 gets dominated by 1, 6 gets dominated by 5, 4 gets dominated by 2. So these ones nobody dominates. So this is the first front. This is the second front. That's the third front. So you see how nicely they're lining up with the whole Pareto front? So if you emphasize this more than any of this, your GA will come and eventually converge there. Now let's say I have added this constraint. That makes this part infeasible anymore. Infeasible now. It's no more feasible. how will the domination structure change with this principle? Now, no infeasible solution can be on the first front. Why? Because any feasible solution will dominate it. Okay. So 1 and 3, which was on the first fronts, now are infeasible, but they cannot be on the first front. That's why, because 4 or 5 or 6 will dominate it. So what members will be in the first front now? 5 and that's it? 5 and 4. Because 4 and 5 do not dominate each other, 6 gets dominated by a feasible member 5. But nobody dominates 4 and 5. These 3 members, without the constraints, would have dominated 4. But with the constraint, they're infeasible, so they cannot dominate a feasible point by this definition. So 4 and 5 becomes non-dominated, which is the level 1. Which is the second level? 6. Third level? Now we are all having all infeasible, and the way it's done, which one has smaller constraint violation? That means which one is closer to the boundary. So 2 is the next, and then 4, and then 5. So previously we have 3 fronts, now we have 5 fronts, and the hierarchy is 4, 5 in the first front, 6 in the second front, 2 is the third front, 1 is the fourth front, and 3 is the fifth front. Okay. Now you see how they are lining up. This one is lining up according to this Pareto front now. Now the Pareto front just moved here. Okay. So you see how nicely it's lining up. So you have pressure to go towards the red line from here. You have pressure to go towards from here as well, because 2 is better than 1, 1 is better than 3. So you have a kind of gradient for going towards that. So from both sides you are coming to the Pareto front. Everything works here without adding any parameter. So that's the nice thing when you think properly, functionally of how you can achieve all these. You may not need any parameter if your thinking process is right. Again, I cannot show you the simulation, but what happens is this point comes and kind of crowds around this non-dominated front here. But yeah, okay. So these are some of the algorithms I wanted to tell you, and the handling of constraints that I wanted to tell you. Now, after we got the front using, let's say, still solving 2 and 3 objectives, I got a front by this method. I am now trying to make a decision and choose a point, right? So how will you do? So one thing I'm saying in this slide is that I could do a priori decision making like the generative methods, where I already tell you, not generative. Generative means I'm still finding the whole front, but I'm going to do just the weighted sum or the epsilon constraint. So I'm making a decision right in the beginning. When you do that, let's say you told that I want 70% importance to the cost and 30% importance to comfort. And I can pose, because this is minimization, maximization, I may have to convert this and get into one composite function with W1 being 70, 0.7 and W2 being 0.3. And I optimize. I will get one of the points on the Pareto front here. Okay? But you see, let's say that is point A. And I have no idea about point B, point 1, point C, any of the other things, because I have not found those things. I've just found one point. Now, it will be something in my mind saying, I told the person to do 70-30. What if this was 69-31? Would I have gotten completely different results, or slightly in the neighborhood, or 71-29? I have no idea. And I feel, again, bad to go and ask him to do this, right? Because this optimization is usually done by junior people in a industry, right? Because it takes a lot of time. You have to formulate, you have to call a software, and decision making is done by the senior people who are more experienced. They can give you these numbers like 70% importance on cost or something. So the whole process may end up with a hitch that, oh, maybe we could have done better or something, right? It's really nice to find a set of points first, get an idea of what are the trade-offs. What is the range of F1? What is the range of cost that you can get in a car? What is the range of comfort that you can achieve? And what are these relationships, so much cost with so much comfort? Analyze, and then it gives you a lot more information to then choose a solution. You are informed. You are making an informed decision. Okay? You will always be happy that you have seen quite a few solutions that are possible, and you have chosen the right one. Right? So a great example that I kind of assisted to these people, but I was not part of the team, where they used NSGA to solve this problem. This is a spacecraft trajectory optimization, where the main people were from University of Illinois at Urbana-Champaign, and they worked with Jet Propulsion Lab of NASA. So what they were doing is they were trying to send spacecraft from Earth to Mars, Jupiter, many places. So what should be the trajectory? In any of such cases, there is more than one criteria that you have to consider. One thing was, I want to get there as quickly as possible. And obviously, when you understand the problem a little bit, if you want to go there quickly, you have to really take a lot of fuel, because you have to adjust your speed as you get there. So you cannot take a lot of mass which is to be delivered at the planet. If you are landing in the planet, you cannot deliver. You have to take a lot of fuel. So that's the trade-off. So they wanted to optimize for minimum time and maximum mass delivered at the target. Looks like there's a trade-off. So they used our NSGA method and found this Pareto front. Let's take this solution 44. Okay, you start on certain date in Earth and you reach Mars on a certain date after a year. So it's 1 year, some months, 1 or 2 months. Okay, and this is the trajectory. And you take about 700 kilos of mass delivered there. Okay. Now, being a mission manager, you want to see, okay, what is the other trade-off solution? So 73, let's take that over here. That's a little more than 2 years. So 1 more year from here to there, and that's why you see it's taking another round, right? But then now you can take about 160, 70 kilos more. So 2 more persons you can take, or 1 person, another equipment, or 2 equipments you can take. So you can take about 170 kilos more. So that's really 100 kilos more, no? Or 170 kilos more. Yeah. So it's about, so that's the trade-off. But then you have to wait 2 years, 1 year, 1 more year to get there. So now you decide as a mission manager, is it worth waiting for 1 more year to be able to take 170? Because I can give you other solutions. You wait 6 months, 1.5 years, I can give you a solution. Then you can take about 100 kilos more. Maybe that's okay for your mission now, and you choose that. Okay. But let me show you 72, which is also on the Pareto front. So all these points are Pareto front, which is here. Now it's 3 years, 2 more years from 44. And look at that. And how much weight you can take more? It's, I think, 3 kilos more. So even I can say, no, don't wait 1 more year to be able to take just 3 kilos. This is in the noise. But this is part of the Pareto front. If you're doing a weighted sum, if you're doing an epsilon constraint, any of those methods, your weight could be such, your 70, 30, what you have given could be such that it falls in one of these points here. That becomes the optima. You will only get that point, and you will never know in your life that you made a bad decision. You could have done 73, which is much quicker, and just sacrificing by a kilo or 2, you could have reduced the time by 6 months. So this kind of applications actually shown the importance of first learning how the front is. Where are the trade-offs? So where are the trade-offs in this problem? Here. Here's the trade-off, because see the nicely it's going up. So I could do 6 months and there's 100, so I can just go take another 6 months, but I'll be able to take now 1 more extra person and maybe a few other stuff. So that's a trade-off from where I am, but this is not a good trade-off, although it's part of the Pareto front. There is a slight slope. So this is where we get away from mathematics and get to practice and say this part is not to be made decision. But how do you know it unless you find it, right? So these applications gave importance to EMO, and there was this surge of applications that came out. If I look at my NSGA-II papers and where people are citing, they are hardly from computer science anymore. They are from different application areas, from space, from chemistry, physics, things that you never thought that they will apply this. But most of these problems will have multiple objectives to make decision. You cannot just consider one thing. Okay, there are always conflicting stuff. Then you need to know what are my possibilities. As soon as there are conflicting objectives, there are a number of solutions that will come as optimum, and they are conflicting. So if you find them and then figure out where to make decisions, where are the good trade-offs, you can keep with them and analyze. It's not an easy decision even to decide that here, but then here there are about 20 different solutions. Which one to take? It's not easy. That's where you need to do group decision making. And a lot of algorithmic methods are also available, but they are always aided with the preference information that the users have. Okay. We have done it with this mine company in Australia, Evolution. So they have 4 objective capabilities actually. So they provide you different solutions of how you should mine, and allows the user to choose based on based on these things. But you see here, when you have 4 objectives, one of the ways we show is that you see these circles, each circle is a solution, but they're of different size. The size tells me the 4th objective, okay, because it's difficult for me to show you 4 objective space, right? But 3 objectives are F1, F2, F3, and the size is the other one. So as you go from one point to the other, size big means bad for that objective. So they have eventually chosen in one of the applications these compromise solutions. This can be all projected into each of these. So they have, you can rotate the whole thing and you can see what the trade-offs are. The key thing is finding these trade-off points and then making a decision, okay, based on what you are sacrificing versus what you are gaining. Okay, let me just say one thing here, because this could be useful all of your, graduate students and teachers. So once you find by NSGA-II or any EMO methods a set of points, EMO method is like another algorithm, right? So as I said, that you need to verify. One of the ways you can verify in multi-objective scenario is do a single objective optimization of each of the objectives. So if I minimize cost only by another optimization. So one thing are these circles which are NSGA-II points. Now I only take the cost and all constraints objective and cost objective and all constraints and minimize, I should get that point, right? So let's see if I get that. So in this case, I did that minimization, I found that star point. Then I minimize only deflection by neglecting cost, and I get that point, that star. So this way I have said, oh, my NSGA-II front, the ends are covered. The ends, what NSGA-II gave me, these 2 objective also gave me the same. Now I do several epsilon constraint. I set up an epsilon here, set up an epsilon here, epsilon here, epsilon here, epsilon here, and do 1, 2, 3, 4, 5, 6 epsilon constraint runs. Again, single objective. And I put those points on my NSGA-II. I see they are falling on top exactly. Now, these are ways to have confidence in your result to say that not all of these optimizations can be wrong, right? So that NSGA-II is wrong, each of these epsilon constant is wrong, and they are supporting each other. Most likely that they're all correct, and that's why they're supporting each other, right? So it's just a way of doing more than what you're supposed to do, support from other knowledge that we have from here, and show that, yes, this could be the front, because these are practical problems. I have no way of knowing where the actual front is, okay? But if I have verified few points and they seem to be falling on a smooth curve, I have no doubt that these are also very close to Pareto optimal fronts, right, when so many things are matching. So I really recommend you to do these additional studies if you're writing a paper or solving an industry problem or your thesis problem. Don't just end up with NSGA-II front and say, hey, NSGA-II is very well known and here is what it gave me, okay? You can always doubt it, okay, and then come back with this single objective optimizations that we know from the classical literature and verify it. Okay? So that's the one thing I wanted to tell you. For decision makings, there are 3 ways to do. As I said, decision making means choosing one point. First is, of course, a priori, which I have said. First, the multi-criteria decision making, MCDM, then an optimization, which is like the weighted sum and epsilon constraint, NCM. There are many, many methods. There are books written on them. Second approach could be a posteriori, like the EMO approach. We don't ask for decision making anything in the beginning. We first find the front, then choose, then do MCDM. We were very ambitious in the beginning. When you do 2, 3 objectives, we could still do, because you can find a good representative set of points. But if I have 10 objectives, how many points shall I find to represent the 10 objective Pareto surface? At least 1,000, 10,000 points we need, 5,000 points we need to show a 10-dimensional surface, right? 2 objective is fine. I can have 50 points and I can get a good representative set. But 10 objectives, it's exponentially, you need more and more. Now, does the decision maker has time to look at 10,000 points solutions? No, they cannot. They don't want to. So this philosophy of first finding the whole front and then making decision falls after 2, 3 objectives. You can focus. You can get all these points, and then what you can do, you can say, I'm going to cluster them and find only 10 points out of that. So the extreme points and maybe 1 or 2 points intermediate. Or if the decision maker tells me, I have all these supporting points now, 10,000 points, but now I ask some questions to the decision maker saying, I got this range. These are the ranges. I'm not going to show you 10-dimensional front, but I've got these ranges. Cost can go from this to this. and efficiency this to that, so on and so forth. Are you interested in looking at certain part? These are some things they can do, because they're always saying, they said, okay, go down to cost between this and this, efficiency between this and this, and then you filter your points and get maybe 4 or 5 points and show it to him. So this is one way you can get there after the a posteriori approach. But there are some very new methods coming up. This is another star you can put if you're interested in doing research in this area. This is really a fertile area. There's only a couple or 3 algorithms that are suggested so far. Interactive approach. So what this is that you do decision making while you're optimizing. So it's not one or the other in a serial manner, but it's all together.
So if the Pareto front is dynamic in nature, non-stationary, then I think this will...
Then this will also work pretty well. Exactly. Okay. So for a priori approaches, as I said, there are books. I've just given you a few names. Reference point is very popular. Light beam is another popular one. Some of these things are also popular. AHP is really a very, very popular method. Nimbus from Kaiser-Meitner is also very popular. So these are popular approaches. Okay, so as I said, let me just talk a little bit about the reference point, because that's a nice way to do things. So reference point means you have no idea of the front, but you have given idea that there are 3 objectives or something. In this case, let's say 2 objectives. Then I'm asking you a question, right? Where do you like your solutions? Because the front is huge. You say, okay, I've got few aspiration points. So that means if this was my cost and this is my waste, both I'm trying to minimize, I give you that I want a cost of 0.1 and a waste of 0.8. I'll be happy with such a solution if you have. This is something sometimes decision makers can do, a combination of function values that they are targeting. So these are target points. I call them aspiration points. And in the literature, they call them reference points. And you may not be sure that this is the only one you are interested. You may have some other combinations of F1, F2 that you may give, let's say 3 or 4. But once you have given them, then basically you are asking the person who is doing optimization is, give me, if these solutions, give me the Pareto front solutions that are close to these points. Most likely they are not achievable because there doesn't exist. You are too optimistic. So basically we are asking, give me a car that will cost like 2 lakhs of rupees and a comfort of 80%. It's not possible, right? Nobody can come up with such a thing. To get 80%, you need to spend at least 5 lakhs of rupees, let's say. So, but you want it in 2 lakhs. So, what you do is this point, if it's in the white space, means you cannot achieve it. All the gray space means you can achieve it. So then you say, okay, give me on the Pareto front. You still want to be on the Pareto front, still want to be optimal, but give me the points that are close to it. Now, this is a little tricky situation. This one, your aspiration, I can give you that because there are solutions here, right? But I can even give you better. So then the decision maker says, hey, that's given better, so give me better. So although this one is achievable, if I find better, I would like to give you that. So this is still my target for that point. And this point is target. So if I don't use this preference information, I would have found the entire Pareto front, because this is the entire thing is the Pareto front. But once you give me these reference points, my target is not to find the entire Pareto front, but only these 3 patches, because you're not interested in here. This doesn't interest you, these combinations of F1, F2, or these ones, or these extremes. Doesn't interest you. You're interested in this. So I can only find this. So this way, computationally, it will be quick, and I give you points where you are interested in. So there is a reference point method that does that, and we've solved it many different problems. There is another one called light beam, but this is, of course, with the reference points in 3D. This reference point gives you this patch. This reference point gives you that patch. So instead of finding the whole surface, we will just find these patches over here by NSGA-II. So we have modified NSGA-II in 2006, which we called as reference point based NSGA-II. There is a light beam concept, which is in principle very nice. You have a Pareto surface for more than 2 objectives. You take a torch and you light a part of the Pareto surface. So you need to now describe how you're holding the torch. So what is the mean direction? What is the angle? These are all related to trade-offs that you're interested in. Okay? And the main direction of the torch says the importance of all the objectives. So these vectors you can define, and the torch we used here is triangular looking, and we can, so the 2 torches you can put simultaneously, multiple also you could do with our NSGA-II approach, and you can find these points instead of finding the whole Pareto front. So this is also quite popular, the light beam search. Here is a reference point based idea showing you some results. So I'm going to skip now some of these. Okay, we'll just do a little bit of few things now. Sometimes, as I said, you are not interested in the whole front. There are several ways to do it. One is a reference point. The other is with the cone domination concept. We talked about the domination, right? When point A dominates this entire region, if you are minimizing F1 and F2, the entire region gets dominated by A. But you can open this up like this. You say A dominates now a bit more region. In that case, if this was your convex front, it only works for convex front. Okay, if this is your convex front, with this domination, entire front would have been non-dominated. With this definition, only this part will be non-dominated, because this point, if I put these lines over here, this matches that, and another one there. So this point dominates this line here and that line, all the inclusive points here. It dominates. So this part is included in the domination range of that. So this point dominates this part. So by making it wide, you are saying, I'm not interested in the whole front. Give me the intermediate part. By keeping this one flat like that, vertical, and only opening this one, you are saying, give me this part of the front. And by keeping this straight and widening that one this way, you are saying, give me this part. So now, how far you go with the angle depends on how much front you are going to get. Okay? So these are called guided domination. You are changing the domination principles to get only a part of it. Unfortunately, it only works for convex fronts. Non-convex, it will not work. Here are the results. Here I did these two lines, and you see only I get the middle, although the whole thing was Pareto front. Here I did vertical and this line, and only this part I get. Okay, so that gave us some idea about parallel. I'm not sure if I have those slides here. Let me just quickly see. Probably not in this slide. So it gave us ideas of distributed computing, because some of you are interested in that. So if you have multiple processors, to each processor you supply a cone, a different cone. So let's say processor number 1, I supply vertical with an angle of 45 degrees, let's say. That is the definition that processor 1 should use. So it's expected to find this part, right, where the tangent here is that 45 degree line. Next processor, I do 45 degree here and maybe 30 degree here. So that will find the intermediate part. And the third one, I give vertical, sorry, I give horizontal and 30 degree here. So this is going to find this edge. So with 3 processors, I have now distributed my task of finding the whole front. Each processor will find only a part. Let them do it independently, and at the end I collect and I get the whole front. So that way I can do very quickly, right? And I also introduce migration intermediate. So it's not just they're independently running, but after a few generations they share where they are. So if this part is difficult to solve, maybe very steep or something, very few solutions are here, but this part is easy to solve, it can send its best point here. Okay? And when it recomputes it with its own thing, those are new good information coming. So if this part is easy to find, that information can be exploited here, and you can speed up that process. So that you can have this implicit parallelism. So all kinds of things you could do when you understand the whole process of this division of task. Okay, there are other methods. There are some a posteriori approach. One of the things people use is this. Once you find the front, okay, the set of points by an EMO algorithm, you go and find the ideal point of this. So this point and that point put together, and I find the ideal point. Here I'm calling as a reference point because they call it as a reference point. And then what you do is you normalize the F1, F2 space. All these points you normalize. So this becomes 1 and this becomes 1 over here, and this is 0, 0. Now you go and see which one is closest to my, with a Euclidean distance, which one is closest to my origin. Lot of people, particularly chemical engineering, they do a lot of multi-objective optimization in process plan, design, and everything. I've seen this again and again. Many papers, they draw this kind of a line saying, I'm choosing the closest one from there. So that's their way of making decision and choosing one point. Okay. But this distance measure you can change, and then it's called compromise programming. You can use a generic LP norm, you can decide what is the P, and then you may have different answer. The other way, which I like very much, and we are really developing a algorithm for this now, is the marginal rate of substitution. What that is that for every point, you look at its neighbor, Now that you have number of points, you can do all these. Every point you go towards neighbor and look at how much gain you are making by unit sacrifice. So if I go from here to there, which objective am I sacrificing? Say I'm minimizing F1, F2. When I go from here to there, I am improving on F1. F1 gets better. F2 gets sacrificed. F2 gets worse. So this divided by that gives me the gain versus sacrifice. How much gain I am getting per unit sacrifice. Go also here. When I want to go from here to there, which is the gain? Gain is this, and sacrifice is that. So this by this would give me the gain by sacrifice. Then I can look at, on an average, how much gain and sacrifice, gain by sacrifice I'm making for each solution. Maybe one of them out of that makes that the highest. That means for unit sacrifice from that solution, I'm gaining the largest. And that's a good point for me to go for, right? So because it's all about trade-off, and this idea actually uses the trade-off information. Then there are other concepts like pseudo-weight and everything. There are many methods for a posteriori. These are after you found the set, then how do I choose one? There are algorithmic ways as well. Ultimately, it has to be decided or dictated by the decision makers. But if there are some obvious points, like with respect to trade-offs and all that, you can then reduce that set even and go to the decision maker with that reduced set. So this is an area which is fuzzy. Not much work really has been done with the EMO concept, this a posteriori idea, not the optimization part. That is all EMO. But how do you then, because many of the papers in EMO you'll see, the last page before conclusion is the front. And then they say nothing, and then they say we found this front, our front is better than other fronts. But if it's an industry problem or practical problem, I would be interested in seeing at least one more page to say how they're going to make a decision and choose one, right? That's really interesting to me. Is it the trade-off? Is it that distance, or is it some other thing? I don't see that, unfortunately. But maybe that's a secret for industries, and they don't do that. But let me tell you the time that I have, 1 or 2 minutes, about interactive methods that I just mentioned, where you don't do it optimization decision making or decision making optimization, but both together. So our idea is this. Let me go back to this figure first, and then I'll come back. So let's say I have optimized for up to about 20 generations. I've got 2 objectives. I've gone 20 generations, and I've got some points. I've got, let's say, 50 points. But from them, I do a clustering, and I choose 5 or 4 of them which are well distributed, because the first time I'm doing it, right? I take those 4 points, go to the decision maker, which in this case could be my boss, who can make decision, and I'm just a junior person. I cannot have that liberty to make decision. So when I go there, I give him these 4 points, and I say, do a pairwise comparison. So compare 1 with 2, and can you tell me, is 1 better than 2? Because I'm giving him the x values and also the f values, so they can look at completely and figure out. This may take a few minutes or a few hours or a day, but let him decide and give me. And he may do 1 with 2, maybe 3 with 4, and 1 with 5, and says, oh, I'm bored. I don't want to do anymore. I don't have time. That's also good. Whatever information, even if it does 1, it's good. In this particular case, I've got the information. Let's say this one is better than that. 2 is better than 3. So better. So in rank wise, 1, 2, 3, 4, 5. You see how the decision maker has told me? Okay. So here he's done a complete ranking, but it may not be that complete to use this method. Now I come back to my desk, and I try to come up with a value function. Okay, that will be a function of f1 and f2. It's basically a function of f1 and f2 now, which will fit this ordering that the person has given me. So basically, I'm trying to model my decision maker with a mathematical function. This is very scary, but for our purposes, we do that, and we modify it as we go along, because we don't have the decision maker with us at every generation. I would have liked that, but since the person is not available, we have to model him somehow so that we can use the next few generations, right? How do we model? Our very simple, the first paper we had was a very simple value function like that. It's a 2 linear function. It's a bilinear function, as they call it. There are 4 parameters, k1, L1, k2, L2. So what I do is I try to solve a problem. Do I have it here? Yes, I have it here. So if you had told me 1 is better than 2, okay, then I will do this way. the value function of the point 1 minus the value function of the point 2 should be at least epsilon, greater than equal to 0, but greater than equal to some positive value epsilon, for all ij pairs satisfying pi better than pj. If you said, okay, the decision maker could have told me, hey, 3 and 4, they are so wide, I cannot make a decision which is better. That's also an information, and I come back and do that. The difference in the value function of the two, absolute difference, is less than delta v, and delta v we put here 1/10 of epsilon. So we put 0.1 times epsilon, but you can put any other. Okay, and then we maximize epsilon. So what we are saying is that choose, it's a 4 variable problem. So choose for 2 objectives, k1, L1, k2, L2. These are my variables for that optimization problem. So I came back from the information, I need to solve an optimization problem now to model him. Okay, that optimization problem has 4 variables, k1, L1, k2, L2. So this is the variable here, this is the problem here. I am maximizing epsilon such that these constraints are satisfied, and each of these constraints involve the decisions that the person has given. So I'm saying the fact that he said 1 is better than 2, my value function should be such, that means my k1, L1, k2, L2 should be such, so that this difference is very, very high. So it's very clear to me that 1 is better than 2. The places where he said, no, I can make a decision, their difference I would like to make so small that I can't even see them. If I draw the value function line, contour line, I can't even see them. So when I actually optimized, I get a value function. When I make the contour now, it looks like this. Now you see, and higher the value, the better is the value function. So you see that rank 1 goes with the highest value function, then second, then third. So this says my optimization worked, and I could separate all these 4 points with the value function. Okay, I have another example here where the decision maker said 1 is better than 2, 2 is better than 3, but 3, 4, and 5 I cannot make any decision. They are so widely apart, I cannot make. So we make that their difference should be very small. So now look at, I found a different value function now where it honors that. So 1 and 2 there's a big difference, 2 and one of these has big difference, but between 4, 5, and 3 I don't have much, I can't even see the difference. Okay, so you can tell me anything that P4 is better than P1, P1 is better than P2. This optimization will try to come up with a function shape that will honor your things, but not always it's possible because the points are situated in a way that it cannot do it. In that case, you get epsilon and 0 or negative. Okay, then we kind of blame the decision maker, saying he is not rational. He's giving inconsistent result, inconsistent decisions. So he's telling 1 is better than 2, but then he's saying maybe 5 is better than 2 or something, or 5 is better than 1. Then I'm having difficulty mathematically finding a model that will fit all his decisions. And sometimes decision makers in the beginning do not know, okay, and they become rational once they see the solutions that are coming in. But the important thing is, if you can do it, do it. Otherwise, you go in the order of preference the decision makers gave you those values and start to drop some of them till you find a rational model to do that. So it's basically modeling the decision maker. And then we're not just modeling the decision maker. From there on, next few generations when you are doing, it's utilizing this function. So it's not original NSGA-II anymore. Our goal is to not find the whole front. So now we'll give preference to points that are maximizing this value function. So we throw in the value function in our NSGA-II, and then we achieve this. So I'm not going into the detail because of time, but this is a simulation on that. You see, I'm starting with this. After every 5 generations, we are going to the decision maker here. And decision makers tell in some way, and we move, and eventually the whole process goes to, this is the entire Pareto front. But the decision maker has guided us to get to one point eventually. Instead of finding the whole thing, you just found the point that decision maker has guided you to come. And in these cases, some reviewers will tell, can the decision maker change their mind? Because once you have reached here, he may want to give it kind of another ideas. So can it move? Yes, you can actually move from here to there. Your decision maker is totally guiding the whole thing. Your value function is every time, see the value function shapes, they're changing with generations. So this is one way we thought that decision making and optimization can be clubbed together. Okay? So we are kind of partitioning the whole optimization by going intermediately to the decision maker and then asking for some preference. I've got some criticism for these as well, because people in the industry says, if decision maker knows that you are going to the person with non-optimal results, because these are non-optimal, right? These are far away from the optima. He would not like to see them. The person would think you're wasting his time. Okay. Also, he may have difficulty making decisions because these are not optimal solutions. Some of them may not make sense to him. So there are some criticism like that, but I really haven't had the chance to apply to any industry to really get a feedback of how they would think. So this is still in the academic stage. But currently what people are doing in industry is still getting the whole front, but because they are restricted to 2 and 3 objectives, and then making a decision. But as soon as they go to higher objectives, they cannot really find the whole front because there are too many. Then you need to go in for such things, because these are also very quick methods, right? Yeah.
So instead of going in the earlier stages, instead of going to the decision maker, if we just use a fuzzy logic device.
You can do, but you need to be guided by what is a good preference information, because this is no more a math problem. Any of those Pareto optimal points you can take from a mathematical point of view. All of them are optimal. Now you need further information which is outside your optimization problem, some personal preference, some company preference, some trade-offs. So those are not mathematical. Those have to come from decision maker, and you don't know how they make decisions. It's from their experiences. So you have to involve them. You could do it with a fuzzy way. Maybe all these things that we are doing, you can introduce fuzzy, but you still need some information from the decision maker. You cannot be completely automated. Another reason for going to the decision maker, as you do, is a psychological one, and which I found in my work before is very, very true. I mean, many of you may not have worked in industry yet, but this is absolutely essential. If you have a great idea for the problem that you have been solving many, many years or something, you should not go to your boss and say, sir, I got this design, or I got this solution. What do you think? It's a human tendency to question that. But if you go to a decision maker, your boss, and say, just don't say the last thing. Keep it very obvious that you told here and told there. Let that final word comes from his mouth. How about then this? And then he say, yeah, that makes sense. And then it'll be of acceptance, because that person thinks he has contributed, okay, in the whole process. So if you come up with a very automatically found solution by fuzzy or whatever, and you go to the industry and say, hey, I found this and use this, it just kind of challenges their intellect. They have been working in this for 10, 15, 20, 25 years, and you used an algorithm, and going to them and say, this is the best solution. This kind of, it's not, I mean, if you're in industry, you'll also feel the same way, that where is my experience? I have not contributed anything to this. So this interactive method is a way you can bring them into the whole process. So I call it humans back into the loop. Okay? But while we're in academics, we try to think of automating everything. And then we think, oh, with artificial intelligence, and so we have done a great thing. But you will have very much difficulty in getting it accepted by a machine telling a human what to do. We want to have ultimate authority, saying, yeah, we have contributed in it. So the best way to do is, and again, it fits very well with the multi-objective concept, that you can go to the industry and say, here are 4 solutions that I consider for your problem to be very good. And I have done lots of things. These are the 4 solutions. That person will be extremely happy, because now he's going to make the final decision of which one to choose. He's part of the process. This is how to do these things. Okay? And the multi-objective is a way to do that, because you're never finding one solution. So I think everything is falling in place. I mean, if you look the psychologically point of view, the problem being having multiple criteria, you just work with the algorithmic issue, but don't make that final step. And this allows you as a framework. So I'm not talking about the hierarchical process, analytical, but this is also, when you have 4 or 5 options, most likely the decision maker, if it is little algorithmic, they are going to be using AHP to finally make a decision. It does a lot of pairwise comparisons and do that. You can look at it in the literature, but if the decision maker can simply call some of his other department heads, sit together with those 4 or 5 solutions and make a decision and tell you what to do. Okay, so we stop now, but let's see with this information what can we do in the afternoon. So as I said, we'll have the exam to do, and we'll have to go to the computer lab, right? Have you checked if they're available? MATLAB is there? Okay, good. So we were not going to do any of these assignments, but what I'm going to give you, no, I cannot give you because tomorrow is the last day, right? So we're going to leave with the exercise number 8 and 9, unfortunately. But sometimes you can do those things maybe after the course is over. So in the afternoon, we'll come and go to the lab. Go to the downstairs lab. Is there a room number or? PC lab 4. Everyone noticed? PC lab 4. We go there at 2 o'clock. We spend about half an hour, maybe to 20, 30, 35 minutes. What you do is those assignment problems, I think, that come from NSGA is also there, so you can try to solve the NSGA problem. But I haven't had the chance to demonstrate you that. But I was thinking more of the exercise 5. Exercise 5, I had 2, 3, 4, and 5. Why don't you try to do it yourselves? And those of you who have done it, then you can move to NSGA-II code and try to then get back to the last one, exercise 9. Okay? So start with exercise 5, then move to 9. So we will come after 30, 35 minutes over here again and write the exam. Okay? And then that's it for today. Then exam syllabus is what you've covered up till now and the last 2 classes. Okay? All right.